say useful things. Okay, so so let's go over the solution to test 2 briefly here. So first of all, I converted it to a system, matrix, normal form or whatever. And so that will give you lambda squared is 4, which means lambda is plus or minus 2, right? Minus 2 gives me this system, which suggests that 1 minus 3 is a good eigenvector. Of course, you could also have 1/3 and minus 1, or minus 1/3 and 1. There are many choices, but something like that. Let's see here. This one, the other eigenvalue of 2 gives me this, which just says that the components of the eigenvector are equal. So 1, 1's a nice choice. There's your general solution. I think a lot of you got this, or at least close to it. You know, if something went wrong with the characteristic equation, of course, that's the most troubling thing. This I'm a little, I'm not, something feels wrong about it. I haven't found my error yet. But this is something we worked out, 2 fundamental matrices. So like this is a fundamental matrix. It's just taking, you know, e to the minus 2t, minus 3 e to the minus 2t, e to the 2t, e to the 2t. Those are my 2 solutions from problem 1. That gives me a fundamental solution matrix. We proved that 2 fundamental solution matrices are related by multiplication by a constant invertible matrix. So if you take this and you put in time equal to 0, that gives me that the identity matrix is that constant matrix times x of 0, which tells me that the constant matrix is actually x inverse of 0. But that's easy to calculate because x of 0 is 1 minus 3, 1, 1. So I can calculate the inverse of that 2 by 2 matrix, multiply by x of t, and that should be the matrix exponential. If I did it right, I got the diagonal matrix e to the minus 2t, e to the 2t. It feels wrong to me. I don't know where my error is, if there is one here. Okay, I'm just saying there might be an error here. I don't know what it is. So some of you got approximate answers here or something, but you know. More of you missed this one, which is a little bit disturbing to me. We did some ones like this in class. Maybe I didn't have enough homework on it. I don't know. But it's pretty simple. We just take the Laplace transform of both sides. I have initial condition 0, so we don't pick up any other extra terms there. Laplace transform of little g is big G, divide by my characteristic polynomial. That gives me this. And then convolution finishes it, right? So the Laplace transform, inverse Laplace transform of that is 1/2 sine 2t, because I needed 2 upstairs for the sine, right, 2t. And then g of t is the inverse transform of big G, and there's the convolution. Of course, you could have also written the integral of g of t minus v times sine of g of, you could have written the integral from 0 to t of g of t minus v times the sine of 2v dv. That would have been the same. There is the fact that the convolution is symmetric. The formula doesn't have to look exactly like this, but that said, I think some of you had exactly this formula, at least a few of you, which is good. Hooray. This one's tougher. Let's see here. So I take the Laplace transform. It gives me s squared big Y minus s because y of 0 is 1. Minus 0 because y prime of 0 is 0. And then plus 3. A lot of you, very popular mistake, not to distribute the 3 over to this minus 1. Very, very popular mistake. In all years of differential equations, your year was not an exception. Let's see here, 2y e to the minus pi s over s is the Laplace transform of that guy. So I bring over my s, I add 3 to both sides, factor out my characteristic polynomial, then divide. I face 2 related but distinct partial fraction decompositions I need to figure out. The one for s plus 3 over s squared plus 3s plus 2, which works out to, did I? Never mind. Sometimes I remember back to something you did correct but different than me that's based on a mistake, and it messes with my head. So anyway, that gives me a 2 for A and a minus 1 for B, which gives me this. Then this partial fractions, I've got an S. I got a cubic, which means I need 3 things for my partial fractions decomposition, and then the usual math It gives me a is a half, b is minus 1, c is a half, which gives me this. And then I use the inverse transform theorems. That gives me 2e to the minus t. This gives me e to the minus 2t. 1 half e to the minus t. Remember, we have to shift t minus pi and t to t minus pi. Some of you had e to the minus t and 1 half e to the minus 2t here. That's wrong. The argument has to match the unit step function, which multiplies it. That's part of the theorem. Again, very popular mistake going back over the years. Really a very, very popular mistake. If I could bet on mistakes that differential equation students will make, I could make some money. Unfortunately, it's a very, very limited gambling racket, which doesn't really have anybody else betting, so oh well. Are we supposed to gamble? I forgot. Are we allowed to gamble? Is gambling for or against it? I don't know. When I was little, my dad had a long debate conversation with somebody else in his Sunday school about whether or not gambling was permissible for Christians. It's a big thing. I forget what they decided. We could bet on it. Sorry, stupid. There's lots of different ways to solve this. You could have found the eigenvectors. That wouldn't have been wrong. You'd have found something like 1i for a complex eigenvector with complex eigenvalue plus or minus 2i here, if you'd done it that way. And even so, you should still come back to these solutions. I mean, the solution is the solution. It's unique given initial conditions. So we can't agree to disagree here. You got to get this, or if you don't get this and you're right, then I'm wrong. We can check if I'm wrong. Let's put in time 0. Time 0, I'm supposed to have x of 0 is 1. Sine of 0 is 0. Cosine of 0 is 1. X equals a 1. Woohoo! Y of 0, is it 3? Yep. So, yeah, odds are not in your favor. What's that thing we used to say? May the odds ever be in your favor? Go on.
What is it 2t, like instead of just t?
Because we end up with s squared plus 4 in the Laplace transform. If we look at the matrix, it's 0, minus 2, 2, 0, which gives me lambda squared plus 4, which factors to plus or minus 2i. The zeros are plus or minus 2i. That's why I get a 2t. Does that make sense? Yeah. But anyway, it's a mixed bag here. Some of you got it. Some of you looked at it and like, what's this problem? That's disturbing to me. This should not be that. I mean, this is like, a fastball straight down the middle. I mean, you should see this one. Should not be surprising that I'm throwing this one at you. This is a pretty standard problem. Anyway. This one here is really just asking you if you've understood the theorems that we've gone over. In particular, the magic formula. This is a chain of generalized eigenvectors with eigenvalue 3. So like u1 is an eigenvector with eigenvalue 3. u2 is generalized eigenvector order 2. Pops out that. This is generalized eigenvector order 3 because it's linked to that. So that will give you these 3 terms. This is a complex eigenvector with eigenvalue 7 plus 2i, which gives me e to the 7t. Cosine A minus sine 2tb, and here's the imaginary piece of the complex solution over there, like we derived. So I think about half of you got the first part of it, but I don't know, something about when I ask the question this way, it is somehow enough divorced from your experience that you guys can't see the way through this sometimes. But I hope now that you look at the answer, it's like, oh, I knew that. Yeah, I hope you have that feeling. If you don't, sorry. And then number 9, find the complete power series solution. So that means summation notation and such. Let's see here. So differentiate 2 times, multiply by 2x squared. Don't forget the 2. A lot of you forgot the 2. I mean, it's like, let me rephrase that. You got like, there's a 2 here. Yay. And then there might even be a 2 in this step. But somehow, by the time we get down to here, the 2 is gone. I don't know why that is. Not all of you, but a lot of you, like 2 or 3 of you, just somehow lost this 2 on the way to the recursion relation. But it's there. And so, yeah. And so recursing, I get something like this, minus 2 to the k, a sub naught over 4k times 4k minus 1, dot, 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 8 times 7 times 4 times 3. And then, of course, the a sub 2 and a sub 3 are 0, as are all their related compatriots. Add multiples of 4 to those, they're also 0. On the other hand, 4k plus 1, it gives you this pattern, minus 2 to the k over 4k plus 1 times 4k times 9 times 8 times 5 times 4. 1 or 2 of you simplified this, and I think your simplification was good. I'm being lazy, though. One of you tried to start this sum at 0. That's problematic because k equals to 0 puts 0 here, which is hard to divide by. So that's why I have to put the 1 out here to pick up the k equals 0 term. In contrast, k equals 0 here is harmless. It just picks up, oh, wait a minute. We'll take a point off my test. Goodness gracious, look at that. 4k, k equals 0. No, 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 no. No, sir, no how. I should have had k equals 1 here. And let's see here. Is that already? That is the k equals 0 term. I should just have a 1 here. I don't know why I did that. Actually, I do. I was really sleepy when I wrote this. But that's my excuse. But that should definitely be a 1. Yeah. Some of you had about half of this right, so I give you about half credit. Some of you had about 85% of this right, so I give you 85% credit. Some of you had about 20% of it right, so I give you 20% credit. I mean, there is a wide spread. Some of you did none of it, so I gave you 0. But there's a lot of different things I saw here. But by and large, the great majority of you know what you're supposed to do and just probably ran out of time to flesh out the details. Which means on the final, if I ask a problem like this, you'll probably just nail it to the wall, right? So that's good. I think what I'm saying is there's a lot of hope in everyone who attempted the problem, even people who just did a little bit and got 5 points. What you did for 5 points was actually the right kind of thing to be doing. So anyway, any questions? Yeah.
I don't know if you said, did you go over 7?
Go over what?
7
7
and
and
9.
You jump straight to 9 from 6.
Really? Scanner. So if you're thinking about purchasing the Canon 490 printer, scanner, copier combo, it has a top feeder, but the top feeder is, well, yeah, less than reliable. All right, let me turn on the lights. I guess I have no choice. Thank you. Well, I was going to post this. I mean, I will post this solution when I get a chance, but apparently I need to rescan it. All right, here we go. Come on. Don't need this laser anymore. Problem 7. We had x squared y prime prime plus 3x y prime plus 5y equals to 0. I told you x is positive. Find the real solution. Well, I should have said find the real solution. It should be understood I want you to find real solutions unless I say otherwise. So characteristic equation is this for the Cauchy-Euler problem. So I let y equals to x to the r as usual. And so that gives me r squared plus 2r plus 5 equals to 0, which gives me r plus 1 quantity squared plus 4 equals to 0, which tells me that r is minus 1 plus or minus 2i. So my solution then is y equals to c1 x to the minus 1 cosine of 2 log x plus c2 x to the minus 1 sine of 2 log x. There you go. Using our standard technique of picking off the real and imaginary part of the complex solution, x to the r. This is now camouflaged. I didn't realize it until just now, but like I'm it like disappears. It's just I just look straight at it. I can't see it. So sad. All right. So let's see here. That one, you guys, if anything, probably the you messed up the quadratic equation, right? Most likely. I forget what happened there, actually. I was dismayed by the general inability to find the radius for the singularity problem on the quiz, by the way. Like, I saw many different wrong answers. You guys need to be more careful with complex arithmetic. I think there is probably all of you would benefit from just finding a page of complex arithmetic problems and just practice until you have it worked out. Because you guys are very shaky on arithmetic with complex numbers. And I was told by an engineering professor, some of you who will have to suffer his classes, that that matters to him. So it probably would be in your vested interest to work out that issue. If not for my class, for his. Let's see here. But I guess if you're not electrical, who cares? All right, 3y equals 0. I didn't say that. Let's see here. I don't really want to work on all of this because we have other things to do. I will post a solution, okay? But basically, we just I'll just collect some of the central features here. I gave us that y prime of 0 was 0, right? So y will be equal to a sub 0 plus a sub 2x squared plus a sub 3 x cubed plus a sub 4 x to the fourth plus dot 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 dot, as a sub 1 is y prime of 0 by Taylor expansion, and that's 0. So I don't need a linear term from the outset because of the initial condition. And so you work that out. Eventually, you should get that a sub 2 is minus 3/2 a sub naught. A sub 3 is 0. A sub 4 is actually 5/8 a sub naught. Some of you wrote as 15/24. That's cool. 1 minus 3/2 x squared plus 5/8 x to the fourth plus dot 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 dot. There you go. That was the answer. Again, I have more details I'll post once I have a chance to sit and watch my scanner page by page. See, it gives you this false sense of like it actually did it right until you actually go and carefully look page by page and then find out it's a lie. Okay, anyway, any questions? Well, don't ask me questions about the details here, but they are routine and they're like the ones we've gone through. All right, so finally, the last kind of problem. So let's talk about Laplace's equation. So just a little background from electrostatics. We have the divergence of the electric field is equal to the charge density divided by epsilon naught. This is Gauss's law. All right. And I'm thinking about an electrostatic situation, so there's no time dependence. So what that means is we can capture the electric field as minus the gradient of the potential. Or I'll tell you what, let me use a big V for voltage. The potential is the voltage function. The electric field is minus the gradient of the voltage function, right? So in the absence of charge, if there's no charge, then what do we get? We have the divergence of the electric field is equal to 0. So if I plug in the voltage function, that's the divergence of the gradient of the voltage function equals to 0, which, getting rid of the sign, gives me that the Laplacian, del squared of V, is equal to 0. Now, some people put a sign, SIGN, on the Laplacian, but this is Laplace's equation. The Laplacian, in Cartesian coordinates, this is like V xx plus V yy equals to 0, or in 3 dimensions, xx plus V yy plus V zz equals to 0. These are Laplace's equation. Now, what if you did have charge, by the way? You'd have the Laplacian squared of the voltage is equal to minus the charge density divided by epsilon naught, is what's known as Poisson's equation. Last semester in Calculus 3, I made some effort to develop some theorems which basically show you that if you're given the distribution of charge on some region, then you can solve Poisson's equation uniquely, subject to how the charge appears on the boundary. So essentially, if you're given the voltage and the charge distribution on the boundary of some region, right, and that the inside of the region, simply connected region, is well, it doesn't even need to be that, but in the interior of the region has no charge, then there's a unique solution to Poisson's equation, and that solution is what we call voltage. So basically, if you set a 0 for the potential and you know where all the charge is, you can find the voltage function, and then once you find the voltage function, you can take the gradient of it, slap a minus on it, that gives the electric field. So Laplace's equation is of course interesting. It's basically just Poisson's equation without charge. It's important, though. There's other applications in terms of fluid flow. Laplace's equation also has to do with the steady laminar flow of fluid in well, like a two-dimensional fluid or something like that. All right, so how do we solve it? So we'll just look at the two-dimensional case. Let me find us a good problem to work on. As you have noticed, I don't trust myself to make up problems here. By the way, you can also solve Laplace's equation on things like disks or other geometries where you might use polar coordinates. And if you use polar coordinates, these equations actually become a Cauchy-Euler problem. So there's the Cauchy-Euler problem works up and appears in the polar coordinate problem. And I have an example like that. Let's see here. Let's look at number 1. So this is section 10.7. And so here's the problem. We've got uxx plus uyy equal to 0. And this is going to be on 0 less than x less than pi, 0 less than y less than 1. And we're given the following data. We're given that partial u, partial x at 0 y is partial u, partial x at pi y. Those are 0. And we're also given that u of x comma 0 is 4 times the cosine of 6x plus the cosine of 7x. And finally, we're given that u of x comma 1 is equal to 0. And let's see here. These are both for 0 less than or equal to x less than or equal to pi. These guys are for 0 less than or equal to y less than or equal to 1. Now I find it's helpful for me, before I get lost in the details here, to take just a minute to draw a picture, to try to picture what I'm doing. So this guy here, we're really looking at some sort of rectangle. Do I have the dimensions right? Yeah, 0 to pi for x, right? 0 to 1 for y. So 0, 0, pi 0, up here is the point, pi 1, and over here is 0, 1, right? And what we're saying is we're trying to solve the Laplace equation in this rectangle. And we're given some things, right? Partial u, partial x is 0, and partial u, partial x is 0, and on where? Use some color coding if you don't mind. So these two boundary conditions, where are those? X equal to 0, right? That's this piece and this piece. So if you pay attention here to my analogy, interpretation rather, of Laplace's equation as it relates to electrostatics, what do those initial conditions say? They say the derivative of the voltage in the x direction is 0. What would that tell you about the gradient of the voltage? It would tell you that that would say that the x component of the electric field is 0. So these actually would say that the electric field is 0 on these two edges. You learn that the electric field has to be perpendicular to the edge in the larger study of things. And then on the other hand, we got these kind of wacky, so we got that x1 is 0, so that's just here, right? So the voltage has to be 0 on that edge. And then the other thing we're given, of course, is that it's like this down here, right? So down here it's kind of interesting. So somehow you're going to have a non-constant voltage solution that we find from solving this Laplace's equation. And that's how the voltage would appear on a plate where you had restricted the electric field to be 0 on the edges, and you forced the voltage to be 0 on the top edge, and you forced the voltage distribution to look like that on the bottom edge. This would be what the voltage would be everywhere else if we solved Laplace's equation. Okay, so let's do it. So what we do is we let u of xy equal to x of x, y of y. Now, you'd be like, whoa, but there's, what's the initial condition here? I mean, like, so you have to let go of this distinction between boundary conditions and initial conditions for this problem, right? There's just space and space, right? So there's only boundary conditions here is what it boils down to. Okay, anyway, so what do we get? uxx plus uyy equals to, what is that? That's x prime prime y plus x y prime prime equal to 0. So we can solve that. X prime prime over x equals to minus y prime prime over y. And I suggest that we put this equal to minus k again. Why can I do that? Why is it a constant? Again, function of x, right? This is a function of what? Y by construction, so they must meet in the middle at a constant. You could derive this also by partial differentiating this equation with respect to like x or y and integrating to get that. I mean, there's ways of deriving that has to be a constant. But anyway, let me get to the point here. Okay, so again, we face a pair of ODEs that are related. We face x prime prime plus kx equals to 0, and, interestingly, y prime prime minus k times y equals to 0. It's kind of neat, right? It means that if we've got sines and cosines for one, we've got coshas and sinches for the other, right? There's some sort of back and forth between cosh and sinh and sine and cosine for this problem, supposing k is positive or negative. Okay, but again, the usual song and dance, what does this say? X of, well, x prime, really, x prime of 0 is x prime of pi is equal to 0, right? I mean, technically, these conditions give us directly something like x prime of 0 times y of y is equal to 0. But since that holds between 0 and 1, it forces this piece to be 0. Since this holds for each y between 0 and 1, we're forced to assume that the blue boundary condition is met for the x solution, right? So then, by proposition 8.3.2, we get k equals to n squared pi squared over L squared. What's my L here? Now here you got to be careful, right? There's two different L's running around. There's the L for x, there's the L for y. Which one are we dealing with? We're dealing with the length in the x direction, right? Which in this case is pi, which is nice, because then we get n squared pi squared over pi squared, and our k is actually what? Just n squared. And let's see here, xn is equal to something like cosine of nx, yeah? Generally be n pi x over L, but the pi's cancel. N equals 0 is also possible here, right? Okay, now that we know that, we can go back and feed it to the y equation, right? What does that tell us about y? How do we solve for y now? Very early in the course, I say something like, cosh and sinh are really nice to know about for solving boundary value problems. I was talking about this moment. So we get y prime prime minus n squared y equal to 0. So what are the solutions? Y is equal to something like a sub n hyperbolic cosine of ny plus b sub n hyperbolic sine of ny. And maybe I should call that y sub n to reflect the fact that it's got an n dependence. So I take the product of these two guys, and I have solved at least part of the problem. But I haven't taken care of the blue, the red and the green boundary conditions, the top and the bottom yet. But a blank template then, we'll form a blank template. U of xt equal to the sum n equals 0 to infinity of, let's see here, a sub n cosh ny sine nx plus b sub n sinh ny sine nx. Of course, that's kind of a silly summation to, n equals 0 is a little bit weird. You could, if you want me to, we could start this sum at 1. What would it change? Let me do that. If I start this at 1, what do I have to add? What happens at n equals 0? Oh. I'm an idiot. You guys should stop me. What did I write down? Something is wrong. Oh, there's more than one thing wrong. Oh, no. Did I write t? Really? Oh, just here, though, thankfully. I thought I wrote over there. That would have been more offensive to me. But yes, it's supposed to be a y. Very good. The other thing. Cosine? Right? Because it's the 0 derivative at the endpoint. So I'm supposed to have cosine nx, yeah? All right. I think I've fixed it. Now, when you put n equals to 0, what do you just get? You just get. I'll put it over here. You put it on either side you want. But anyway, there's plus the a sub naught term, you know. Now we can fit. So we want to select. Wish to select a sub n and b sub n to fit data at y equals to 0 and y equals to 1. Which one do you guys want? I mean, we can do whichever one you want first. Which one do you think we should do first? I think I'm going to do the pink one first. Let's look at what is u of x0. What's that give us? It gives me a sub naught, right? Plus what? Plus the sum n equals 1 to infinity. We're plugging in y equals to 0, right? So I get a sub n cosine nx. What's the sinh of 0? Zero, right? So that means the b sub n terms are gone. That's it for our blank template. That's supposed to match the given 4 cosine 6x plus cosine 7x, yeah? So if you look at that, search your heart, you can see that a sub n is 0 for what? For n not equal to 6 or 7, right? And a sub 6 is 4, and a sub 7 is 1. Not too bad. All right, now we still have the data at, so that was my y equals 0 data. What's my y equals 1 data? Come on. U of x comma 1 equals to, well, we just figured out a sub naught is 0. We can drop it. And we also got what? We've got 4. So we've got 4 cosh of 4 cosine of 4. I'm an idiot. N equals what is non-zero? Not 4. N equals 6. So I should do 6y, which is 6 when we put in y equals to 1. Cosine of 6x plus cosh of 7 cosine of 7x. All right. And then we got what? Plus the summation n equals 1 to infinity of b sub n, which we don't know yet, sinh of ny, which is sinh of n, because y is equal to 1, cosine nx. Basically, we're going to use linear independence of the cosine function with different integer multiples. What that means is that all the b sub n's have to be 0, except for those which could be canceled by the corresponding terms that came from the a's. So from this equation that I'm underlining in blue, I get a lot. This tells me that my b sub n is equal to 0 for n not equal to 6 or 7, right? And for n equals to 6, what do I get? I get 4 cosh of 6, right? Plus what? Sinh of 6, well, more to the point here, plus b sub 6, hyperbolic sine of 6, is equal to 0. Because that's the coefficient of cosine 6x, right? That it has to all be equal to 0. This is given to be equal to 0, right? That was part of the problem statement, that it works out to 0. So I've got that, and I also have from n equals to 7, I've got that the hyperbolic cosine of 7 plus b sub 7 hyperbolic sine of 7 is equal to 0. So what's this tell me? B6 is what? It's minus 4 coth of 6, and b sub 7 is just minus the hyperbolic cotangent of 7. Let's see here, let's put it together. So we have u of x comma y equals to 4 cosh 6 cos 6 plus cosh 7y cosine 7x, right? Minus, and I'm going to write it in terms of hyperbolic cosine and sine. So that's, of course, that's minus 4 cosh 6 over sinh 6. And that was sinh of 6y cosine 6x, and then minus cosh 7 over sinh 7 sinh 7y cosine 7x. All right, let's clean this up a little bit. what we have is 4 cosh of 6y. I'll make a common denominator, sinh of 6 minus cosh of 6 sinh of 6y divided by sinh 6. Of course, all of that is times the cosine of 6x and then plus parentheses. The other one is, let's see here, sinh 7 cosh 7y minus cosh 7 sinh 7y, all divided by sinh 7 cosine 7x. But you may or may not know this, there's adding angles formulas for cosh and sinh. So like, you can work it out. I think, if I recall correctly, the hyperbolic sinh of like a plus b is cosh a sinh b plus sinh a cosh b. If I remember that right, then you can look at this and go, oh, so that's really 4 divided by the hyperbolic sine of 6 times the sinh of, I want to say, 6 minus 6y, I think. And then that over here, of course, times the cosine of 6x. And that over there would be 1 over sinh 7. And then we'd have the hyperbolic sine 7 minus 7y, I think. And cosine of 7x. And there you go. That's about as nice an answer as I can come up with. Of course, I'd given you a lot of partial credit in this kind of problem if you just got to this point, you know. But full credit is what I wrote. Especially if I say simplify your answer, you know. Now, the nice thing about the boxed final answer is we can check the solution, see if it actually fits the bill, right? Like, how about up top? It's supposed to be what on the green? 0, right? That's y equals to 1. What happens when you put y equals to 1 into the formula we just derived? Sinh of 0, everything's 0. The voltage is 0 at the top. How about at the bottom? What happens at y equals to 0? Down here. But y equals to 0, we get sinh of 6. We get sinh of 7. Cancels. Cancels. Leaves us with 4 cosine 6x plus cosine 7x, which is this guy. So indeed, this fits the boundary conditions as advertised. You're like, do we have to do all that extra simplification? Well, if I assign you an odd problem in the book, you'd like to know about this. Like when I first worked this problem, I got to what I underlined in green, up to a sign or something. I was close. And then I looked at the back of the book and I was like, what? And then I was like, oh, there are adding angles formulas for cosh and sinh. I learned it at that point. And then I started looking at this and I realized why it's a better answer. Because it just makes manifest the initial data that we wanted. All right, so what made this problem simpler than some of the ones we looked at earlier today? It's pretty simple. The basic thing is that we were given boundary conditions which were already Fourier series of the appropriate type. The 0 series, right? And this is already expanded as sum of cosines. How would we make this problem harder? It's pretty simple. Replace this with something that you actually need to find the cosine series for. You can still do the calculation, right? And you can replace u of x comma 1 with something you can also find the Fourier find the cosine series for. And then you'd actually have to sort through the same math over here, just that you wouldn't have mostly zeros. You'd have some kind of intertwangling, if you will, of intertwining of the a sub n's and b sub n's as afforded by the y equals 1 data. I still think this is a good example. Because we've done enough of the Fourier thing that you probably have some sense of how that would go. And you also know that you don't really want to see me do the details here, since we have like a minute left. I will show you this, though, and then we'll call it a day. Come on. Oh, well. So here, I'll get it. It's cool. Oop. So this is the end of the road for my homework solutions that I have posted there. But I've got I solved some problems here. There's some discussion like we went over today. This is the one we just worked out. You see the difference between what I'm doing now and what I was doing then? When I first started this, I was always working out proposition 8.31 and 8.32 in the context of each problem. Now I'm just sort of shelving those as things we use. It shortens the work a lot, right? Anyway. Yep. So that's what he's got. All right. Yowzers. Oh, here I actually have derivations of the... Oh, weird. That's funny. I've related hyperbolic sine to sine using adding angles formula for sine, and then bogarted it back to the world of hyperbolic sine. This is number 3 I have worked out here with some indication of how the Fourier analysis goes. Fine. This is the one I wanted to show you briefly. Here's the Dirichlet problem on a disk. When you actually look at some of you have my Calc 3, I might have made you derive this. This is the Laplacian in polar coordinates. So if you look at that, that's got a regular singular point at 0. So if you multiply by r squared, it's evidently a Cauchy-Euler problem. And it has to satisfy other things like 2 pi periodicity, right? You're looking for period. You have that periodic boundary condition, which is really different than what we've done. And there's also some assumption about, solution at infinity not blowing up or things like that. But anyway, this one's interesting. You can do things like, I actually have one solved here. But that's interesting and a little bit different. Don't worry, I'm not assigning one of those to you. Just wanted to show you that Cauchy-Euler can come up here. This is a Neumann boundary value problem. Again, I have a solution posted for if you're interested. And then the other thing, of course, is if you were to look at if you were to look at 3 dimensions, you can actually end up with like double Fourier series. You end up with like summation over m and n for 2 things. And there's a little bit in the text on that too. We didn't get to it, but it's okay. So anyway, I'll try to write this thing up for you, have it posted later today. Tomorrow we have the final. We will try to have it in this room. If it's full of pesky teenagers or something, we'll go use the physics lab or whatever. I'll leave a note on the door for wherever we go in case people are late. But we'll find some place and our last classroom interaction tomorrow, yes.
How long do we have for the final?
2.5 the whole time. Yeah.
Still a sheet of notes?
Yep, you are allowed 1 page of notes, front and back.